Yes, hello everyone. So, yes, जी आज का जो हमारा टॉपिक है इलेक्ट्रोकेमिस्ट्री हम कर रहे थे और इलेक्ट्रोकेमिस्ट्री का डेट so announced equation we have done, right? The first, okay. So now next is measurement of electrode potential. So potential of individual half cell we cannot measure. We cannot determine or we cannot measure the potential of a single electrode. What is the reason? Actually, when a cell is set up, only we can determine the potential difference. Like, you know, lone left side oxidation anode and a negative. So when they are connected to each other, by attaching voltmeter like zinc copper, zinc rod is immersed in zinc sulfate or in any zinc salt, and copper is immersed in copper sulfate solution, and salt bridge is attached to maintain electrical neutrality and the electrical connection of the half cells internally. Okay, so to calculate E naught cell is equal to E naught right minus E naught left, or E naught cathode minus E naught anode. Like here, cathode is copper and anode is zinc. The reduction potential, standard reduction potential of each. So to determine E naught value of any one electrode, E naught cell, that can be calculated from the voltmeter. So E naught right is equal to E naught cell plus E naught left, or E naught left is equal to E naught right minus E naught cell. So this is the way to calculate. That means one of the electrode, either left side or right side, one of the electrode, we should know its standard reduction potential before calculating the standard reduction potential of the other electrode. And a single electrode, we cannot measure reduction potential. Okay, electrode potential of a single electrode cannot be measured. That's why we need electrode whose concentration is known and at the same time its reduction potential is known to us, and that is called reference electrode. So we need a reference electrode, and standard hydrogen electrode is one of the reference electrode whose E naught value is equal to 0. E naught value is equal to 0. This is the standard reduction potential. See, in this case, this is the finely divided platinum coated on platinum foil, and this solution is 1 molar H plus ions concentration, and hydrogen gas is bubbled through it at 1 bar pressure. Hydrogen gas is bubbled through it at 1 bar pressure. Concentration of H plus ion in the solution is 1 molar, and finely divided platinum is coated on platinum foil that is used as an electrode. So why platinum foil is used, or why finely divided platinum is coated on platinum foil? Because it will increase the surface area and therefore more hydrogen gas gets absorbed on it. More hydrogen gas gets absorbed on it. Okay, so this is called standard hydrogen electrode, and it's is represented as platinum solid, H2 gas, H plus aqueous, and is assigned a 0 potential at all temperatures. H plus ion concentration plus electron half H2. So see, the standard hydrogen electrode consists of a platinum electrode which is coated with platinum black. Why we coat it with platinum black? Because powdered platinum, that will increase the surface area and therefore more hydrogen gas absorbed on it. Okay, so electrode that is dipped in an acidic solution, and what is the concentration of this acidic solution? 1 molar H plus ions, and pure hydrogen gas is bubbled through it at 1 bar pressure. तो concentration जो है of both the reduced and oxidized form of hydrogen is maintained at unity. This is at 1 molar, means it is also unity. Hydrogen gas is also at a unity, is at 1 bar pressure. That's why it is written as concentration of both the reduced and oxidized forms of hydrogen is maintained at a unity. This implies pressure of the hydrogen gas is 1 bar and concentration of hydrogen ion in the solution is 1 molar. So that is the representation of standard hydrogen electrode. In short, it is called SHE, SHE, and its E naught value is 0.00 volt. Okay, this is about standard hydrogen electrode. Now, next. So at 298 Kelvin, the EMF of the cell, so standard hydrogen electrode, salt bridge, double vertical arrow, vertical lines represent salt bridge, and then second half cell constructed by taking standard hydrogen electrode as anode, that is a reference half cell. Reference means reference electrode or reference half cell. It means its potential is known to us. That's why it is called reference. We refer it. And other half cell as cathode, and it gives a reduction potential of the other half cell. So if the concentrations of the oxidized and reduced forms of the species in the right hand half cell, that is second half cell, is unity, then cell potential is equal to standard electrode potential. Okay, then electrode potential, that is called standard electrode potential. So E naught cell, we have already discussed. E naught cell is E naught right minus E naught left, and E naught left, left means the one where oxidation takes place. Just keep in mind lone. Left oxidation, anode negative. Okay, so E naught L for standard hydrogen electrode, that is 0, you know, because E naught L, that is E naught H plus H2 PT, that is equal to 0, right? So that implies E naught cell equal to E naught right minus 0. So in this way, E naught cell is equal to E naught right. Whatever E naught cell we get, that is the standard reduction potential of right half cell. Okay, for example, to measure the EMF of this cell, cell is given to you, it is PT solid, H2 gas at 1 bar pressure, H plus aqueous at 1 molar concentration, salt bridge, copper 2 plus aqueous, that is again 1 molar, and copper solid. So this is the cell. This cell is given to you. So in this cell, you know, this part, this is anode, is on the left side, oxidation takes place, and it is an anode. And this part, that is cathode, it is on the right side, it is on the left side. Okay, so E naught cell, that is equal to E naught right minus E naught left, and right is E naught copper 2 plus copper minus E naught H plus H2 PT. Okay, So in this way, you know E naught copper 2 plus copper we have to calculate, and this is standard hydrogen electrode. Its value is 0. In this way, E naught copper 2 plus 2 copper, that is standard reduction potential of copper, that is equal to E naught cell. Got it? Yes, beta. Means this is a way to calculate reduction potential of copper. See, to calculate reduction potential of copper, what we did, we just connect copper to the standard hydrogen electrode, that is the reference electrode. Means we have to frame a cell first, because to calculate reduction potential of a single electrode, that is impossible, that cannot be calculated, and this value is 0.34 volt for E naught copper 2 plus 2 copper. It is also the value for the standard electrode potential of the half cell corresponding to the reaction. Okay. Now for zinc, again this is the reaction. We have again framed the cell. Platinum means standard hydrogen electrode is attached, and zinc 2 plus zinc, and its EMF comes out to be minus 0.76 volt. How do we calculate? This is the cell. It is solid, H2 gas, 1 bar, H plus aqueous 1 molar, zinc 2 plus aqueous 1 molar, zinc solid. Now E naught cell equal to E naught, again right minus left, E naught right. E naught right means zinc 2 plus 2 zinc minus E naught H plus H2 PT, and this is standard hydrogen electrode on the left side, and this is zinc electrode on the right side. It is acting as cathode and it acts as anode, and its value it is 0, as it is a reference electrode. Its value is taken as 0. Minus 0. E naught zinc 2 plus 2 zinc, it is E naught cell. Value comes out to be minus, is on the minus side. Okay, that's why we can, when we construct a cell by using zinc, because E naught cell comes out to be negative, that means with hydrogen electrode, zinc should be used as anode, because E naught cell should be positive. Okay. So positive value of standard electrode potential in the first case indicate that copper 2 plus ion gets reduced more easily than H plus. Means if we have this reaction, its E naught value is plus 0.34 volt. And its E naught value is 0. So it indicates as a reduction potential of copper is more than hydrogen. That means copper 2 plus gets reduced more easily than H plus ions. But the reverse process cannot occur. That is, hydrogen ions cannot oxidize copper. That means we can say hydrogen gas can reduce copper ion under standard conditions. Thus, copper does not dissolve in HCl. Means this reaction cannot take place. Means if copper plus H plus to give copper 2 plus plus half H2, or we can write copper plus 2H plus, because it is not the balanced equation, so we can write it like this. So this reaction cannot take place because E naught cell for this particular reaction, E naught cell is negative. But in nitric acid, it is oxidized. Copper is oxidized in nitric acid, but where H plus ions are not used as the oxidizing agent for copper, but nitrate ions is oxidized by nitrate ion and not by hydrogen ion. So negative value of standard electrode potential in the second case. See, in the second case means zinc. In this case, negative value in the second case, it indicates that this reaction, zinc 2 plus H2 to give zinc plus 2H plus, this reaction cannot take place. Rather, reaction taking place is zinc 2H plus, means zinc is oxidized by H plus ions. Zinc is oxidized by H plus ions. That's what it is written. The negative value of standard electrode potential in the second case indicates hydrogen ions can oxidize zinc, or we can say zinc can reduce hydrogen ions. So half cell for a Daniell cell, you can note zinc can be oxidized and copper can be reduced. Left electrode is zinc and right electrode is copper, and overall reaction of the cell is sum of the above two reactions. We obtain the equation as, okay. So EMF of the cell is E naught cell equal to E naught right minus E naught left, that is 0.34 volt minus 0.76 volt and 1.10 volt. We have already done this. Zinc copper cell, that is zinc solid, zinc 2 plus aqueous, copper 2 plus aqueous to copper solid. This is the cell. Calculate EMF of this cell. What we do first is standard EMF of the cell. Okay. So E naught cell equal to E naught right minus E naught left. See, left electrode zinc is oxidized, and on the right electrode copper is reduced. The overall reaction is zinc solid because electrons are already balanced. This is the overall cell reaction. This overall cell reaction. This is reduction half cell reaction, and this is oxidation half cell reaction. Sorry. Above one is oxidation half cell reaction, and this is reduction half cell reaction. So E naught cell is equal to E naught right, that is E naught copper 2 plus copper minus E naught zinc 2 plus zinc. So what is the value of E naught copper 2 plus copper is plus 0.34 volt minus zinc minus 0.76 volt. So it is plus 0.34 volt plus 0.76 volt, that is plus 1.10 volt. This is E naught cell. For zinc copper cell, and that is called Daniell cell. Daniell cell is zinc copper cell. Now it is written sometimes metals like platinum or gold, they are used as inert electrodes. They do not participate in the reaction but provide their surface for oxidation or reduction reactions and for the conduction of electrodes. You know, platinum is used in standard hydrogen electrode. Standard hydrogen electrode, we are using platinum. Why? Because hydrogen gas evolved that should be in equilibrium with H plus ions. So to adsorb hydrogen, platinum solid is used because it provides the surface. Okay. Same is the case with bromine. Bromine electrode, we are using platinum solid for the reaction. It provides the surface for the reaction to take place. And Br negative ion, Br2 liquid. That's why it is written as aqueous. Br2 it is solid, Br2 liquid, Br negative aqueous. The overall half cell. Written as standard electrode potentials are very important, and we can extract a lot of information from them. Because the values of standard reduction potentials that are used to select particular electrode as a cathode or anode. Now, if standard electrode potential, what is standard electrode potential actually? It is standard reduction potential. So if standard electrode potential, it is greater than 0. That means its reduced form is more stable compared to the hydrogen gas. For example, in case of copper, so copper 2 plus is reduced by hydrogen gas to copper solid, and hydrogen gas itself gets oxidized to H plus ions. Okay, so that means when copper 2 plus ions are present and hydrogen gas is bubbled through it, then it turns into copper solid and hydrogen gas gets oxidized to H plus ion. So it means, what is the reduced form of copper? That is copper solid. So its reduced form is more stable than the hydrogen gas. That's what it is written. Similarly, if we are dealing with negative reduction potential, for example, zinc, its standard reduction potential is negative. E naught value of copper plus 0.34 volt. That's why its reduced form is more stable than hydrogen gas, because standard reduction potential of hydrogen is only 0. So if copper has positive reduction potential, that means its reduction potential is more than that of hydrogen standard reduction potentials. That's why its reduced form is more stable than hydrogen gas. Now come to zinc. So if we talk about reduction potential of zinc, its value is minus 0.76. Obviously, in the presence of hydrogen, zinc gets oxidized because its reduction potential is low. So zinc in the presence of H plus ions, zinc is oxidized and hydrogen is reduced. Okay, same if we have fluorine. Fluorine gives F negative and H2 into 2H plus ions. Okay, so see, if standard electrode potential is negative, then hydrogen gas is more stable than the reduced form of the particular species. Hydrogen gas is more stable than reduced form of that particular species. So first is the example of copper and second is the example of zinc. So it can be seen that standard electrode potential for fluorine is highest in the table. Fluorine has highest and lithium has lowest reduction potential. So that's why fluorine gas has the maximum tendency to get reduced to F negative ions. Therefore, fluorine gas is strongest oxidizing agent, and fluoride ions are the weakest. Fluoride ions are the weakest reducing agents. F2 is strongest oxidizing agent, but fluoride ion is weakest reducing agent. Fluoride ion is weakest reducing agent and fluorine gas is strongest oxidizing agent. Now come to lithium. Lithium has lowest electrode potential. So what it means? Lithium ion, that is the weakest oxidizing agent, and lithium metal is most powerful reducing agent in the aqueous solution. Why is it so? Because in first case, fluorine standard reduction potential is highest, so it has very strong tendency to gain electrons. That's why forward reaction is favorable. That means fluorine can gain electrons, but fluoride, its tendency to lose electron is minimal. That's why fluorine, those species which gain electrons, they are strongest oxidizing agents, and those species which lose electrons are the reducing agents. So here fluoride has least tendency to lose electrons. That's why it is a weakest reducing agent. Now come to lithium. Lithium has lowest reduction potential. That means its tendency to reduce is very low. That's why it has tendency to lose electrons. That means lithium is strongest reducing agent. What is reducing agent? The one which can reduce others and itself gets oxidized. Itself gets oxidized. Or simply those species which lose electron are reducing agents, because these electrons are gained by someone which gets reduced. That's why lithium is reducing agent. Okay, but lithium ion is weakest oxidizing agent. Okay. Lithium metal is most powerful reducing agent in aqueous solution, and lithium ion is the weakest oxidizing agent. So as we go from top to bottom, so standard electrode potential decreases as we go from top to bottom. Standard reduction potentials or electrode potential decreases, and with this oxidizing power decreases. And on the left, right, and increases the reducing power of the species on the right hand side of the reaction. So electrochemical cells, they are extensively used for determining the pH of solutions, solubility product, equilibrium constant, and other thermodynamic properties, and for even potentiometric titrations. We will use electrochemical cells. Yes, this is the question for you. How would you determine the standard electrode potential of the system? This system Mg2 plus 2Mg. Yes, beta. How do we calculate? Yes, how would you determine the standard electrode potential of the system, that is Mg2 plus 2Mg? Have you any guess? Yes, beta, any guess? So just attach this electrode, because you know standard electrode potential of the single electrode cannot be calculated or cannot be determined. It is impossible. So just we attach this electrode to the hydrogen electrode. We'll attach electrode to hydrogen electrode. See. Mg2 plus Mg, that we will attach to hydrogen electrode. Okay, so this is the cell. The reaction is Mg, sorry, because left side oxidation takes place, so reaction is like this. So E naught cell is E naught right minus E naught left. And what is E naught right? E naught H plus minus E naught Mg2 plus Mg. And you know, this is standard hydrogen electrode and its value is, you know, 0. So E naught cell is minus E naught. In this way, we can determine the standard electrode potential of magnesium. Okay. In this way, we can calculate the standard electrode potential of magnesium. Right? Now, next one. Can you store copper sulfate solutions in a zinc pot? Yes, beta. Please tell me. Can you store copper sulfate solutions in a zinc pot? Found, beta. So, you know, if we compare the reduction potential of zinc and copper, see, reduction potential of zinc, it is minus 0.76 volt, and copper, if we say its reduction is easier as compared to zinc and its oxidation is easier. So that implies when zinc is stored in copper sulfate, then zinc gets oxidized because its reduction potential is low, and copper sulfate, zinc is converted into zinc sulfate. That means it is dissolved, zinc is dissolved, and copper is reduced. Okay, copper 2 plus turns into copper solid. That means zinc pot gets dissolved. That's why, as copper can oxidize zinc, therefore copper sulfate cannot be stored in a zinc pot, cause copper can oxidize zinc. This is the reason that copper sulfate cannot be stored in a zinc. Yes, that's right. Okay. Next question. Oh, this is the this is related to the table of standard electrode potentials and suggest three substances that can oxidize ferrous ions. Fe2 plus ions. You know what is the reduction potential of iron? That can oxidize. Okay, sorry. That can oxidize means Fe2 plus electron, sorry, Fe2 plus to give Fe3 plus electron. Means we will suggest three substances that can oxidize ferrous ions by consulting the standard electrode potential table. I will show you the table. So you can suggest by your own. Electrochemistry. Yes, beta. So suggest. Actually, you know, Fe2 plus to Fe3 plus. What is the value? E naught value of Fe3 plus to Fe2 plus. It is plus 0.77 volt. So any electrode above it can oxidize like silver. What is the value for silver? Silver value is plus 0.80. That means silver can oxidize. Fluorine, yes beta. What is the value? Plus 2.87. That means fluorine can oxidize. Then chlorine can oxidize. .36 volt. Even bromine can oxidize. That means silver, chlorine, bromine, they can oxidize. Okay, got it? Because their reduction potentials are 'Muskan Sharma'. What is the difficulty, beta? Tell me. So say Fe2 plus to Fe3 plus. E naught value is Fe3 plus to Fe2 plus, that is plus 0.77 volt. So any electrode, any metal, or any species having reduction potential more than that can oxidize Fe2 plus ions. Okay, so that's why silver, chlorine, bromine, even oxygen, they can oxidize it. Okay, any doubt up to this? Yes, beta. That's all for the day. Thank you so much. But any difficulty you can write in the comment section. I will definitely solve it.